Hey, hi guys, good morning. Hope I am audible.
Yes, sir, you are audible. Morning, Srikant.
Good morning, good morning. Sorry guys, I didn't expect my schedule would be that hectic here. So yesterday I reached my place at 11 p.m. So I went out morning at 8:30 and then came back at 11. So today also just now I reached my place. So it's going to be very hectic now here. Uh, but anyways, okay, so I'll try my best, to cope up with this course, even if I'm taking off. Don't worry, guys. I'll cover the topics. Okay, so you need not to worry on that part. All right. So okay. So in continuation with what we discussed last week, so we discussed about confidence interval estimation. So we discussed about a scenario where we have the information about this population variance. So, in case if we do not have that information, then how can we go and calculate the confidence interval? We'll see in today's class. So, the only thing is like if we don't have this information, if sigma is unknown to us, we now substitute uh, this standard deviation. Sorry, the standard deviation with the sample standard deviation, which is known as S. Okay. So we know that in the population parameter, when we talk about mu, so in sample, we talk about X bar, right? If we talk about variance in population by sigma square, here we represent it by S square. Here the standard deviation is denoted by sigma, then here in sample, it is denoted by S. So here, as we do not have this information about the population standard deviation, so here we go and consider the sample standard deviation. So if we are considering the sample standard deviation, then even we have to go and refer to different distribution, not the standard normal distribution. So here we go and refer to the t distribution. Okay, instead of standard normal distribution. So those are the two major changes what we have to consider when we are going with this particular scenario where the population variance is unknown to us. So if we are going with a sample standard deviation, it introduces extra uncertainty. Okay, because S uh, is a sample standard deviation, and generally when we consider the sample, there would be some level of uncertainty, there would be some level of sampling error included into the sample, and on top of that, okay, we are considering some sample statistics, so it will add some extra uncertainty. So that's the reason we, instead of going with the standard normal distribution, we go with the t distribution. Here if you refer to these both the distributions, here the probability or the range of the probabilities values would differ from standard normal distribution. So for example, if this is Z distribution and this is T distribution, so the 95% of uh, the 95% confidence interval in the Z distribution would be wider, while the 95% confidence interval in the T distribution would be narrower. Okay, so that would be the difference, okay, in these two distribution. Now coming to the formula. So here, this is X bar plus minus margin of error. So here the margin of error formula is, instead of Z distribution, if you remember in the previous class, when we are considering the Z distribution, it was Z alpha by 2 into sigma by root n. So this was a reliability factor and this was a standard error. Now in this case of T distribution, the margin of error is T n minus 1, I'll tell you what is n minus 1, alpha by 2. Instead of sigma by root n, here we will go with a s by root n. So this is my standard error, and this would be my reliability factor. So that's the difference. So here, what is this n minus 1? So in statistics, n minus 1 is called as degrees of freedom. In short, we call it as DF. So degrees of freedom, something you can relate at as in sample. For example, it's a sample. And in sample, just for as a for an example, just take that I have elements as 2, 1, 3, 4. Okay. So 3 plus 1, 4, 4 plus 4, 8, 10. 10 divided by 4. 10 divided by 4 would be how much? 2.5, right? So if let's suppose this is my sample, sample mean is equal to 2.5. Here n is equal to 4, which is sample size. Now, the degrees of freedom is nothing but sample size minus 1. So why we go with the degrees of freedom and why it is minus 1? See that now just take an assumption that, okay, we know the sample mean. That sample mean is 2.5. If we have the sample mean as 2.5, how much degrees of freedom do we have, to choose the elements in the sample in a random way? Okay, in some with some random selection. So for example, this is an empty box and I have to pick up the values from this particular box and drop it here. Okay, so here out of four values, I have a freedom to select only 3 values if the sample mean is fixed. How? So for example, this is an empty box. I'll go and pick out of 4. I have a freedom, okay, to pick any one. So let's suppose I picked 1. And after that, I have again 3 values left. So again, I have a choice there. Let's suppose I picked 2. And third time I picked 3. Now I'm left with only one element now. And if I have to fix this mean as 2.5, I do not have any choice other than picking 4. And that's the only value which I can pick. So here I do not have a choice. I have to go with 4, but here I have a choice. So here what basically, to reduce the uncertainty, generally in statistics, rather than going with dividing uh, uh, the denominator with the number of items or the sample size, generally we go with degrees of freedom, which is sample size minus 1. So that that is the kind of an explanation people give, but people have done a lot of research. So instead of dividing it by sample size, they generally go with sample size minus 1, and that has given a better results, okay, in the statistical analysis. That's the reason degrees of freedom is considered as an important factor when we are dealing with sample. So here in this t distribution, we have a table where we have to look into 2 different values. One is the degrees of freedom and the second is at significance level, which is alpha. So earlier, if you remember, in the Z table, we have just considered this alpha value to find out the Z score. But here, to find out this T score, along with this alpha value, we also require a degrees of freedom. Okay, and in the table, I'll show you, in the table, we refer to these 2 values to estimate this particular T score. And this T score is exactly the same way, how we have used the Z score. In the same way, we have to use this T score. Okay, and that will give us a confidence interval. So this part is very clear. We don't have the sigma in this case. So we are going with a standard deviation, which is S. So by which, we are calculating the standard of error. Here, instead of the Z distribution, we have to go with the T distribution. And this T distribution, we go with, uh, 2 different factors. One is degrees of freedom and another is significance level. And rest of the calculation is exactly the same. If you see this particular population parameter or population mean lies within this confidence interval from X minus this margin of error to X bar plus this margin of error. So in between this particular range, your population mean lies. Okay, that's what this confidence interval estimate provides us the information. So let's go and so here is the number of the observations that are free to vary after sample mean has been calculated. So if your sample mean is fixed, then in particular sample, the values, only the n-1 number of values are free to vary. So the location or the place or the sequence of those values, only the n-1 values, okay, they have a freedom, to vary. Otherwise, the last one, it has to be fixed. Okay, so yeah, so if you look at this particular table, here you will have this degrees of freedom. So let's suppose if your sample size is 15, then degrees of freedom would be 14. So you pick up the degrees of 14 here, and this is your significance level. So generally we go with the industry standard. The alpha is usually it is 0.05. That means 5% risk, and your confidence level would be 95%. Okay, typically these are like industry standard. Okay, in most of the cases where in the problem the alpha is not provided, there we go generally with 0.05. Okay, and here we can pick up that alpha value. Okay, and from here on the row wise, we pick the degrees of freedom, and then we can calculate the t-score. So uh, this is for one tail and this is for two tail. I'll tell you later. Okay, what is this one tail and two tail when we discuss about hypothesis testing. Okay, so what are the steps you have to follow? First, in the problem statement, you have to check whether the population standard deviation is provided to you or not. If it is not provided, then you have to go with this method where you have to consider the t distribution rather than z distribution. And you have to use this particular formula, which is x bar plus minus margin of error, where the margin of error would be t n-1, which is where n-1 is nothing but degrees of freedom, and alpha by 2. Okay, and now this is wrong. This is s, not sigma. And instead of sigma, we have to go with s by root n. Now we will pick up one problem. Okay. So let's suppose my random sample of size 25 has a sample mean equal to 50 and the standard deviation equal to 8. So here I just have all the information related to the sample. So here they're asking form a 95% confidence interval for this population mean. So here degrees of freedom, we can easily we can go and calculate, which is n-1, 25 minus 1, which is equal to 24. Okay, and here the t value, we have to go and look at degrees of freedom equal to 24 and alpha by 2 equal to 0.025. Let's go and look at here. 24 and 0.0.25, it's 2.391. Let's see if that's the case. It's showing 2.0639. Okay. Oh, sorry, this should be one tailed because we are taking alpha by 2, right? So alpha by 2, if you remember, so this is alpha by 2 and this is alpha by 2. Okay, so we have to look at one particular tail side, right? So here the alpha by 2, we are going and finding out at one single side, which is one tailed. So at degrees of freedom equal to 24 and alpha equal to 0.025, which is coming out to be 0.064. So plus minus 2.064 is my t value. Okay. So 2.064 on the left hand side and 2.064 on the right hand side. Okay, into my standard error. Standard error is your sample standard deviation divided by square root of your sample size. So through which, we can able to find out the lower limit of the confidence interval and the higher limit. Now this is the range. Now instead of this, if you go and use Z distribution here, take it as an exercise. Okay, instead of t, consider the Z distribution and see what how much, what range of interval you are getting, okay, if you are going and considering the Z distribution. So typically, in sample, if there is uncertainty is high, so we'll go with a wider distribution. So the T distribution would be wider than your Z distribution. Okay, and what else? Yeah, and one more thing you have to remember, if your sample size is greater than 30 or equal to 30, then instead of T distribution, you can go and refer to Z distribution. Okay, so I think probably it may confuse you, but what it says that in statistics, if your sample size is greater than 30, then based on central limit theorem, if you remember, central limit theorem says that if your sample sizes increases, your data will tend to become normally distributed. So here, larger means in statistics, if your sample size is greater than 30, so if you have more than 30 objects in your sample, then you can consider it as a large sample. Okay, and then you can consider it as a normal distribution, and instead of T distribution, you can refer to Z distribution. So in two scenarios, generally we go with the T distribution. One is if we do not have the population standard deviation information, then we have to go with the T distribution. And in that also, if the sample size is less than 30, then only we go with the T distribution. Otherwise, we can go with the Z distribution. So I'll take a pause. Is this clear, or do you have any confusion on this, guys?
Can you repeat the points one again? We go for this T distribution when sample size is less than 30, and the
30.
first one was population.
Population standard deviation is not provided. So see, if there is
Okay.
a scenario, I'm giving you a scenario. For example, let's suppose this is the only scenario, okay? So now in this scenario, you have no choice other than going with the T distribution. See, first you have to check whether I have the population standard deviation provided to me. In this case, it is not. So we are here only sample standard deviation is provided. And the second check you have to make, what is the sample size? So here, none of the condition is being met, to use Z distribution. Okay. Now, instead of 25, if I make it as 35, then I can go with the Z distribution. Okay. And
Even if we don't have that sigma,
even
we
if
should go for
even if we do not have the population standard deviation, if my sample size is greater than 30, then I can go with a Z distribution. See, here you need to understand why exactly we're going with the T distribution. If I have shown, if you remember this point, so basically, if I'm going with the sample standard deviation, then basically it's introducing the extra uncertainty. So when it is an extra uncertainty in the data, generally we consider that the data is not following a normal distribution, because if there is uncertainty, so your data is not symmetric in that case. In statistics, it has been proved that if your sample size exceeds 30 data points, generally it will follow a normal distribution. That's an assumption typically. So if we are assuming that my data is following a normal distribution, then I can go ahead and use the Z distribution as a reference distribution for calculating my reliability factor. If my sample size is less than 30, so then I consider that the distribution is kind of not normally distributed, and then I will go and consider the T distribution, okay, instead of normal distribution. And see, I will show you one point here. Okay, so in this case only you see, typically at 0.025, what was the Z score, if you remember? Did we get in the last class? It was plus minus 1.96, right? If you remember.
Yeah, correct.
Yes.
Yeah, 1.96.
Yeah. Here, if you see, it is more. Okay, it is not 1.6. It is slightly more than 1.96. Okay, it is 2.064. Okay, you can consider it as 2.1. So now, where we were multiplying the standard error with 1.96 when we were using the standard normal distribution, here in this case, in the t distribution, we are multiplying it with 2.19. So in that case, my interval would be wider. So if there is an uncertainty, higher uncertainty, I will go with a wider confidence interval. For example, let's suppose if you are not certain how much time it may take for you to reach your home, if somebody at your home calls you and say that, okay, how much time will you take? Would you give the answer with a wider interval or a narrow interval? That's a question. Okay. Now you tell me where you are not pretty certain about how much time it may take. So would you give a wider range or would you give a shorter range or narrow range?
Wider range.
Wider range, right? You may say that, okay, I may take roughly 1 hour to 3 hours, right? Why you will say that? Because you are not very certain how much time it may take, right? So if you are certain, then you will give a very, very specific range saying that, okay, I may take somewhere, 15 minutes to 18 minutes. You'll be that much precise. Okay, your range would be much narrower. So as we are talking about sample and we do not have any information about the population, so here we go with the t distribution. And with this t distribution, what happens is we are adding some little bit of extra factor or the magnitude of that reliability factor would be little higher than the z distribution, and because of which my range would be little higher when compared to the z distribution range. Okay, so that's the only difference. Okay, so after this, so that is about finding out the confidence interval for mean, for population mean. Now here, the next point is now confidence interval for the population proportion. Now, what is this population proportion? So mean we understood, okay, if we have to comment on something on the quantitative basically variable, and if it is a quantitative variable, then it has to be in a numeric format, right? It has to be continuous. For example, temperature, for example, sales, for example, the quality parameter. So whichever data which is measured in a numeric, in numbers, in the form of decimals or in the which is continuous variable, there we go with the mean. Okay. Now comes the I can call it as a qualitative factor. So for example, if I say how much proportion of people are English speaking, okay, in this particular community. So here I'm going with a proportion. Okay, so there is no measurement as such. I'm just taking the proportion of those people. I'll just take a count. Okay, and then I will take how much percentage of that count is out of the entire community members, and that would be my answer. So in that case, again, I may require some kind of a confidence interval if I'm going with a sample. So for example, I say that how many people are English speaking, in this particular region. So I'll not go and go and check every member in that particular region and then validate whether that person can speak English or not. Instead of that, I will go with a sample because why sampling is important, and why we go with sample, right? So if I'm going with a sample, and we have also seen that instead of going with a point estimate, it is always better, to go with a confidence interval because that's because the confidence interval will minimize the sampling error. Okay, so if in case I have to comment on the proportion, okay, in any of the circumstances or in any of the scenarios, there I will go with this this technique, okay, where I will use sample proportion, and based on the sample proportion, I'll calculate the confidence interval for the population proportion. So it would be exactly the same the way we have done it for mean, but here the formula may change a little bit. Okay. So the interval estimate for the population proportion can be calculated by adding an allowance for uncertainty to the sample proportion. So what is that uncertainty here? It is nothing but a margin of error. So that uncertainty which is coming out because of the sample, that's something, okay, we are trying to measure, and that uncertainty we are kind of adding, okay, to our point estimate. Okay. So now let's see, for this proportion, what is the formula? So here, the standard deviation, okay, the standard deviation here for the population proportion is denoted like this, okay. So it is, so for example, in this population, P is this. So now you can consider this P as English speaking guys. What would be this proportion? This would be 1 minus P. So if in any population, the English speaking people are, let's suppose, 20%, then non-English speaking people would be 100 minus 20, which is 80%. Okay. So the product of these two proportion, P, which is the proportion of our interest, into 1 minus of P, okay, it will be the product, which will be the numerator, and then we will divide it by the sample size, and then finally we'll take the square root of that. That will give me the standard deviation. So basically this is, inside one is called as variance. Okay, the square root of the variance is nothing but my standard deviation. So we'll calculate the standard deviation, and for the sample, instead of P, it would be P hat. So if you remember, in the population parameter, the proportion is denoted by capital P, and in the sample, the proportion is denoted by small p hat. Okay, that's basically the difference. And now it's if you can relate this particular formula with the confidence interval for population mean, it is kind of exactly the same. Okay, similar. So it is the point estimate. Okay, so point estimate is nothing but is the sample statistics, okay, which you have calculated on your sample. So for mean, we have used X bar, and for proportion, we will use P hat. Okay, minus, this is my reliability factor, RF, and this is my, you can consider it as standard error, which is here in this case, which is equal to standard deviation. Because in the standard deviation also, we are using this sample size. Okay, now this is the formula, okay, which we have used for population proportion. That's all. And this we know how to calculate, right? So we have to refer to the Z table, and at alpha, if the alpha is given, then based on the alpha, we have to go and find out the Z score. And this P hat, generally we calculate from the sample. So let's suppose I want to find out how many people can speak English, then I will take the sample randomly, okay, from that particular community or that particular region. Let's suppose I've taken 100 of the people as a sample. So in that 100 people, I will go and check, how many people can speak English. And that would be my P hat. Let's suppose out of 100, 25 people can only speak English, then P hat would be 25%. So which is 0.25. Okay, and then 0.25 into 1 minus 0.25, which is 0.75. I'll take the product of these two, 0.25 into 0.75, and then divide by 100. Okay, so that would be my variance. Here in this case, the standard deviation is, I'll take standard deviation, which is square root of the variance. That's all. Okay. So there is a condition here, which you need to check. Generally, no one will ask, but for your information, you can just remember. here, if your sample size is 100, let's suppose P is 0.25, and this is your 1 minus P, which is 0.75. So what it would be, 100 into 0.25, 0.75, which is 25 into 0.75. Whatever comes, that has to be greater than 5. So it is basically a condition which in statistics we kind of assume, because in that case only we consider that the sample is large enough, at which, we can go and consider this Z distribution. If it is not satisfying this particular condition, then we cannot calculate the confidence interval, because in that case referring to the Z distribution will go wrong. Okay, because here the population or the number of uh, objects, okay, which falls in that particular proportion is not big enough, to consider this Z distribution. Okay, so that's the check we have to make. Okay, otherwise now we are good. Okay, so for example, in this case now, a random sample of 100 people shows that 25 are left-handed. So that means I have a sample of 100 people. In that 100 people, 25 people are lefty. Okay, they write and they use left hand instead of right hand. So here the problem is form a 95% confidence interval for the true proportion of the left-handers. So can I go and say that, okay, generally in the world, 25% of the people are left-handed. Okay, like probably, that may not be the correct statement, with 100% confidence level. So rather than giving with the point estimate, I rather prefer going with a range. So here they have asked, okay, with a 95% confidence level, give me the range. So now I'll go and calculate that range. So firstly, I will calculate whether that condition fulfills or not, which is NP 1 minus P greater than 5. So here N is 100. What is P, guys? Proportion of left-handed. Is 0.25, right? 25 people out of 100 into 0.75. So first I'll check this. If it is greater than 5, then I can proceed and I can go ahead with this particular formula, and then I can go and calculate the confidence interval. So here Z alpha by 2, where alpha is equal to 0.05. Because confidence level is 95%, which is 0.95, then alpha is nothing but 1 minus confidence level, which is equal to 0.05. So here alpha by 2 is 0.025, and we know, and we have calculated in the last week, right, at alpha by 2, my Z score is plus minus 1.96. And this we have just now seen, this is the standard deviation formula, okay, which will consider it as a standard error. So 0.25 into 0.75 divided by 100. So now with this, I got this particular range. Now with 95% confidence interval, I can state that somewhere, 16% to 33% of the people are left-handed. Okay, that kind of a statement I can pass, for particular population. So I'll take a pause. Is this clear, everyone? If somebody has a question on the application, then do let me know. I'll give you some more examples. So if there's any confusion on the formula, so don't worry. Okay. Generally, we don't do it by using pen and paper and calculate it manually. So we will have some tool, okay, on which we go and perform all these statistical analysis. So in Python, it is just one single line of code, okay, where you have to pass the data and it will give you the confidence interval. Okay. In any other tools like proprietary tools, again, which is more of a UI driven, there we have to choose the option and pass the data, and then it will give you the results. But now the most important part is how to interpret those results and how to apply these concepts to solve some business problem. Now, see, now this proportion usually we use more number of times. So sometimes to check whether my data is biased or not. It's important, right? So in your data, every category has to be equally represented. Otherwise, what will happen? While training the model, your model may get biased. Okay. So for example, to a kid, okay, if you're teaching that kid to know two colors, one red and second is orange. Okay, let's suppose these are the two colors which you want the kid to uh, recognize. Now let's suppose out of 100 times, like 80 times, you are showing only red color to that particular kid, and you show very rarely the orange color. Then the kid will become biased towards red color. Quickly he can recognize the red color, but orange color possibly he may not recognize properly, because you have given those kind of example very limited number of times. Even that happens, when we even learn, right? When we learn certain subject, if we solve certain kind of problems more number of times, then there is a high chance that you can solve those kind of problems easily. Okay, if you don't practice a certain kind of problems more often, then there is a chance that you may not able to attempt it in your exam. So to check whether your data is biased or not, you can kind of apply this confidence interval on top of that data to see what would be the confidence interval of a particular proportion in your data. Okay, by examining the standard deviation as well as by examining the proportion of uh, that particular category. Okay, so that's a technical implementation of this confidence interval, but at a business level also. For example, now you want to understand how much range of your products are are being produced as defected. Okay, so then you count all the defected items which have been produced in a particular day. Let's suppose that is 20%. Then based on the sample size, you can go and find out the standard deviation, and you can comment that, okay, typically in a day, I'm 95% confidence that the defected piece are somewhere between the range of 25% to 35%. So this will give a clarity to the business people, like, how much quality is being maintained or how much defected piece are getting manufactured. So if it is beyond certain range, then they can go and look into it more closely, and they can take some strategic decisions. So like that, you have multiple use cases around it. Okay, so you can just do a quick research on your side to find out the different kinds of problem statement around this confidence interval. Okay. Any questions? Did
Yeah,
you?
just try to give us some scenarios, where to use what. We have some exercise, we'll get to know more scenarios, where to calculate what.
Okay. So yeah, so I said that I will share you, but yeah, I couldn't. So I'll share those exercises. But at a high level, just understand. Okay. I mentioned you about two different kinds of variables, right? One is continuous variable and second is categorical variable. In your data, if in your sample, rather than calling data, let's suppose sample. Okay, in your sample, if you have to comment something on the continuous variable, there we go and apply the mean, and there we will go and calculate the confidence interval for mean. If we are talking about a categorical variable, definitely on the categorical variable, we cannot apply mean because we cannot do the arithmetical calculation on the categorical column, which is qualitative variable. So there we go and look out for proportion. So for example, gender, male and female. So for example, on my website, I want to understand how much proportion of people who are, how much proportion of female uh, users are coming onto my website. So here I'm talking about the proportion. I'm talking about the categorical column. So in my data, this particular column will have only two categories like male or female. So what I can do, I cannot go and find out the average because I cannot do the calculations there. So rather than that, I'll go with the proportion. So let's suppose my sample size is 100 and in my data, there are 60 females. So that means 60% of the people are female in my sample. But I have to comment on my population parameter, which is capital P. So rather than going with a point estimate, I'll go with a confidence interval. So if in the case, if for the case of for the case of categorical variable where I have to talk on the proportion, and this is the formula which I have to use, to come up with the confidence interval. So this is a very simple way of defining where you have to use mean and where you have to use proportion. On the continuous variable, you have to go with the mean, and on the categorical variable, you have to go with the proportion. Okay, so this you understood, right? Now on top of this, I will give you certain exercises where you will understand the application of this particular concept now. Okay, now in this case, simple, it is very simple, like out of 100 people, it says that 25 people are left-handed. So can we go ahead and calculate the average? Definitely not, right? It does not make sense at all. So here the only thing is left is to calculate the proportion. So out of 100, 25 are left-handed. That means 25% of the people are left-handed. In that case, I'll go with the confidence interval for proportion. So how you have to tackle to any problem is, first you understand whether you are dealing with a continuous variable or a categorical variable. If you understand that, rest everything is simple. If it is a continuous variable, then you have to go with the mean. If it is a categorical variable, then you have to go with the proportion. Technically, did you guys get it? Where to use proportion, where to use mean? That is clear, right?
Yes.
Okay, so I'll give you a scenario. Okay, I'll give you 2 or 3 scenarios. Quickly tell me, okay, what you will use. So, for example, now let's suppose now I'm in Minneapolis. Okay, now somebody, let's suppose you asked me, okay, now what is the daily temperature, okay, of that particular city? So what I will do, I'll take some past data, okay, of last couple of weeks, okay, and take the temperature on a daily basis. Okay, then I'll calculate on top of that, the confidence interval. So in this case, you tell me what measure point estimate will I consider to calculate the confidence interval? Would it be mean or would it be proportion?
Will be mean.
Mean, right? So you will take the temperature, because how you have concluded with this? Because temperature is measured in numerical format, which is continuous variable. So on top of that, I can calculate mean. So that's the reason I will go with mean. Now, for example, if you ask me how many Indian people lives in Minneapolis, if that's the question given to me, then what should I do? How many people in Minneapolis are Indians? If that's the question is given to me, then what should I go ahead with?
Proportion.
Proportion, right? Simple. So I'll take a sample. Let's suppose in the community where I'm staying right now, that could be my sample. And in this particular community, I will count for Indian people. Okay. So, and that would be my sample. And based on that, I will go and find out the confidence interval. So I may say that, okay, it is somewhere between 25% to 35%, and I'm not 95% confident on that. So I think now you got it, where to use proportion, where to use mean. So these are the two major important uh, things, which we use for uh, for making inference about the population. Now after this, we have something on the variance side also, but that is very rare. So that's something, okay, I'm skipping for now. But if you look at this, so confidence interval, majorly we go with for population mean and for population proportion. For population mean, we go if we are considering the continuous variable. Population proportion we go if we are considering the categorical variable. So this population variance for now, I'm not picking up. So if these two are clear, then I think it would be easier for you to understand the hypothesis testing, which we'll discuss uh, in the following classes. So I'll take a pause. Let me know if you have any question on these two areas and these two concepts. Did you understand the use of these distributions? Why we are using these distributions? Z distribution or T distribution? Basically, we use that, to measure the uncertainty, because those distribution will give us the probability. And definition of the probability is nothing but the measure of uncertainty, right? So if I say what is the probability that today it will rain, okay, so if I say 95%, so that means the uncertainty is less, okay, and I'm pretty certain that, okay, it's going to rain, right? So that's the reason I'm saying 95%. If I say there is a 5% chance of rain, so that means I'm quite uncertain about whether it will rain or not. I'm very much certain that it will not rain, but I am quite uncertain whether it will rain. It will rain, right? So that is about probability. So when we are referring to this distribution, these are nothing but the probability distribution. What here we are saying is, what is the probability that I will get this particular value that I am calculating through these distribution, and those values I am using it for my sample, and that sample which I'm assuming that it is going to be a normal distribution. So I don't know whether how many of people are following this. So what this distribution says that, and why I'm explaining it again and again, because if you get this particular concept, rest hypothesis testing in whatever statistical analysis you do, now this is the only funda which we are going to refer with. Okay, if you don't get it now, and for other concepts also, it would be difficult for you to understand. Now I'm saying this is the sample distribution, and this sample distribution I'm referring to Z distribution, which is my normal distribution. So here at 95% or whatever confidence level or whatever probability, at whatever probability, I'm finding out these values. Okay, and these values I'm overlaying on my sample, to find out the confidence interval. So basically, this distribution typically, generally, we use, to measure the uncertainty. As simple as that. Okay, now when we are referring to this distribution, we have to also make sure that what kind of information do we have about the population. If we have some information about the population, then we can confidently go and use this Z distribution. If not, then we have to go with another distribution known as T distribution. So like that, we have multiple other distribution, guys. Okay, in hypothesis testing, okay, I will show you some other distribution. Then slowly we'll understand in what all circumstances, in what all situation, we have to refer what distribution. But for now, just to understand that in for population mean, if population standard deviation is given, then we go with the Z distribution. And this is important, guys. Please remember, because in hypothesis testing, we have a similar test we call as Z test. Okay, and that time we should understand, okay, where to use Z test and where to use Z distribution. If the stand variance is unknown about the population, there we go with the T distribution. Again, in this case, if my sample size increases by more than 30, then I have a freedom to go and use Z distribution. And in this population proportion, we do not have any such thing to worry. Okay, here we go with Z distribution only. Okay, we don't go with T distribution. And here we check that condition, which is NP into 1 minus P, whether it is greater than 5 or not. If it is greater than 5, then only we can go and we can calculate the confidence interval. Otherwise, we cannot calculate the confidence interval. All right. I hope this is clear. All right. So this is just a concept. Okay. And with this concept, we can solve some basic problems. Okay. Where we have to comment something about the population. This is something I'm skipping for now. Otherwise, there's a high chance that you guys will get confused. Okay. Just for now, just understand that for continuous variable, we go with mean, and for categorical, we go with proportion. All right. So now, okay. So after this, I would like to cover probability and the probability distribution. Okay. And once we cover this probability, then we will talk about the probability distributions, other distributions, and then later we will get into hypothesis testing. So now coming to the probability, I think everyone might have studied this probability in some way or the other. Okay, in some of their in their education, right? So now we studied probability, but we don't know the usage of the probability, right? Generally, whenever we have to decide anything, generally in our minds, okay, we use probability, okay, but typically we don't take pen and paper and calculate the probabilities and then we do it. So, for example, gambling, okay, or even for trading, I don't think anybody, does that calculation. Okay, how many times the stock prices increased and decreased. Generally, we go with an intuition, right? Uh, but in most of our decisions, some or the other way, we use probability. So, for example, mm, you have to catch a bus, right? Now to your office. Okay, so now if you have some idea about that, okay, if I go at this particular time, exactly I'll get a bus. Okay, 100% I'll get a bus. And if I go later than at this time, generally I will miss the bus. So what is that? That's chance of, that particular event to occur, right? So you will have certain thing in your mind and unintentionally or based on our experience, we take that decision. Okay, will I get the bus at this time or not? Sometimes what happens is like even if we are 5 minutes late than usual time, generally we have a idea that okay, we will get it. There is a chance that okay, I can get my bus. But after a certain limit, you will say that okay, 100%, I'll not get the bus. So what is that 100%? That is nothing but the likelihood of that event to occur, right? So that's nothing but the probability. So in our real life, where we are taking the decisions, we generally go with the probability. Just imagine when business is taking a decision, they will also generally go with probability. Earlier, the business people, they were going with intuition, they were going with their gut feeling, they're going with an experience. But after this data science being used in the business field, generally the business leaders, they are going and taking the data driven decisions. There they are going and calculating these probabilities and taking the historical data, and then they are taking the right decisions. So now even in the gambling, so I don't know how many of you gamble. So generally in the cricket matches or any other um, casinos and all those things, there also, if you see, a lot of people will show a lot of statistics. Okay, so they will in the casino, what they will do is you go to on any table, they will provide all the statistics that in today's match, how many times this particular number has occurred. So generally, who have that statistic mindset, they will look at those numbers. They will get an idea that okay, what is the chance of winning? If you bet on this particular number, and based on that, they will make a decision. Okay, even on the cricket matches also, what is the probability that today's this particular team will win, right? So all the major decisions in your life also, if you see, it is always based on probability. So that's the application of this probability, guys. Okay, so it is a very, very important and very powerful topic, okay, in statistics and machine learning, and everything, okay, which we are going to study will be based on this particular probability. Okay. Now in this probability, we might have heard about marginal probability, joint probability, conditional probability. That's something, okay, we will go and understand what are those. Firstly, let's understand at a very high level, okay, what is probability? Now this probability is a numerical measure of the likelihood, or you can say that numerical measure of uncertainty of a particular of any event. Okay. So that is nothing but the probability. And you know that this probability would range from 0 to 1, where 0 means there is no chance. Okay, there is no likelihood of any particular event to occur if the probability is 0. If it is 1, that it is quite certain that particular event would occur. So generally, the probability would range between 0 to 1. If I say probability is 0.8, so that means there is a 80% chance of that event to occur. If I say probability is 0.2, then it is 20% chance that particular event would occur. So that's the range of the probability from 0 to 1, and is denoted as P of that particular event, that is probability of that event. Second is, now you need to understand how the events are, okay? If I'm talking about multiple events, okay, then I have to understand whether those events are exclusive events mutually or they are not. So what do you mean by mutually exclusive? So for example, let's take a dice, okay, a rolling dice, the Ludo dice, okay. So in the dice, we have 6 numbers, 1 to 6. All these numbers are mutually exclusive because when you roll a die, either you will get 1, 2, 3, 4, 5, or 6, right? You will not get two numbers together. So here means all these events are mutually exclusive. That because these events cannot occur together. Okay. So and we can also say that the events are independent. Okay. That is known as mutually exclusive. Second is collectively exhaustive. Collectively exhaustive means when I roll a die, I will have an option of only these 6 events. There is no chance of getting any other value apart from 1 to 6. I cannot get 0, I cannot get 7. I will only get the numbers between 1 to 6. So these are collectively exhaustive. So 1, 2, 3, 4, 5, 6 together is considered as collectively exhaustive. These are the only option. These are the only things it may occur. Apart from this, there is no other event which may occur. So if I'm talking about rain or no rain, now you tell me whether these two events are mutually exclusive or not. Rain and no rain.
Yes, mutually
Mutually exclusive. These two events cannot occur together.
at a time.
Now you tell me whether these are collectively exhaustive or not. Can I get any other event apart from this? Either it will rain or it will not rain, right? There is no other third option, right? Either I will pass or I will fail. Either my stock price will go up or go down. Okay, it may stay stable also. That could be a third option, but generally it is like binary. Okay, if it is binary, then it is known as collectively exhaustive. In that way, we generally say that probability of each of these events, if you calculate independently, then sum of all these events will be equal to 1. For example, Boolean for the binary kind of a thing, it is very easy. For example, if the probability of rain is 0.2, then what is the probability of not getting rain, guys? If the probability of rain is 0.2, what is the probability of not getting rain?
0.8.
0.8.
0.8. It is
0.8.
1
Yeah.
minus 0.8. So when the sum of the probability of each of the events is equal to 1, then we call those events as collectively exhaustive. Because the sum of the probabilities of the mutually exclusive and the collectively exhaustive event is 1. Now, mutually exclusive is these events are independent. Okay, that means these two events cannot occur together. Now, tell me the probability of being sunny in a day and probability of getting a rain. Okay, just think once. Can we call these two events as mutually exclusive?
No.
No. There could be a chance that, okay, it could be a sunny as well as I may get a rain, right? So these two events I cannot call mutually exclusive. Now tell me, are these events can be called as collectively exhaustive? So if I sum these two, would I get equal to 1? No. Okay. So there could be another events also. So like probability of not getting rain. Not getting rain could be one of the event, right? It could be sunny and it could be and there couldn't be any rain, right? So that could be another event. So here in this case, I'm just gave you example. In the business terms also, you need to understand, okay, if the person is coming onto your website and not buying a product, okay, is these two events are mutually exclusive or not? Okay, and here and that particular person being female, what is the probability? Okay, they will go and they will drop from your website without buying anything. So here it is, these are events are not mutually exclusive. So these are events you can consider as dependent events. Here, to buy a particular product on your website, a particular product on your website, does it depend on the user's gender? It could be a case, right? Because if you are selling a shirt as well as skirt, right? So buying a skirt could be conditioned on the user's gender. There could be high chance that only the female would buy skirts, right? So in those cases, you have to clearly understand you're talking about what events, whether those events are independent events or dependent events, or we call as conditioned events. If this is a conditioned event, then there is a different formula of calculating the probability. Okay. So for example, winning a match, if the Rohit Sharma is a captain or Dhoni is the captain, so then you have to say that with this combination of the team, how many times it has won. So there we are talking about condition probability. So all that we will understand, but by now just understand if you have 3 events, for example, rolling a die, if we are talking about 6 events, all those 6 events are called as mutually exclusive because you will get only one number at a time and they are collectively exhaustive. Now you tell me for rolling a die, what is the probability of if it is a very fair die, okay, dice, okay, what is the probability of getting 5? What is the probability of getting 5?
1/6.
This one. What is the probability of getting 6?
1/6.
So for every number, it's a equal probability, like 1/6. Now, if you sum all these 1/6 for all the numbers, what would be the sum? So this is for probability of 1, probability of 2. It is equal to 1, right?
1.
6/6, it's 1. So all these events are mutually exclusive. Then we can clearly qualify that all these events are collectively exhaustive and these are mutually exclusive. Okay. So I hope you understood these two terms, mutually exclusive and collectively exhaustive. Anybody has any doubt on this? Yes or no?
Just once more, can you repeat that? Collective, versus mutually exclusive.
See, mutually exclusive means the two events cannot occur together.
Okay.
Can you pass at the same time? Can you fail in your exam? You cannot.
No. Yeah.
Either you will pass or you will fail. So those two events are known as mutually exclusive. Collective exhaustive means, is there any other third option if you're attempting an exam apart from getting pass or getting fail? No, right? Either
No,
you will
there's an
pass or
option.
you will fail. Is there any other option? So for example, machine. Okay. Machine could be in a running condition or could be in a dormant condition. Okay. It may be idle. Okay. Idle or running condition. Is there any other option? No. So
No.
that means these are collectively exhaustive. If you take these two events together, then that is like overall, we will call it as sample space. That's the overall, what do you say, um, options. Okay, there is no any other option apart from that. So in that case, we call it as collectively exhaustive. So if you take all these events together, so those are the only events it may occur. Okay, for example, rolling a die, there are 6 events which can occur, right?
Okay.
If you taking a deck of cards, how many options do you have? How many cards usually we have, in a deck?
52.
52 cards, right? So the whole sample space is 52. So that means there are 52 events which can occur. If I have to randomly pick a card, then I can pick any one card out of the 52 cards. Okay. So if I consider all those 52 cards, then it is known as collectively exhaustive. Okay, together. And picking of any one card, the probability would be 1 by 52. There's a chance. Okay. If I go and add the probability of every card, so that means 1 by 52, 1 by 52, 52 times, the sum would be equal to 1. So in that case, all those 52 events are together known as collectively exhaustive if the sum of the probabilities is equal to 1. So that means,
Okay, got it.
yeah, so total sum of all the events, if the probability is equal to 1, that means there is no any other events apart from those events which can be considered. Okay. Okay, once you hear about certain examples, then you will get even more clarity on this. Okay. So here, when you're saying probability is equal to 1, that means you are very much certain, you're 100% certain. And if it is 0, that is quite uncertain and it's impossible, okay, for any event to occur. That's the range of the probability. If it is 0.5, generally we don't want to get into this condition where we have a probability of 50%. So when you use 50%, if you say what is the probability of winning a team today, can you take any decision if I say that 50% chance? Okay, so neither it is yes nor it is no. If you have to be on the safe side, generally we say that we don't know, it's a 50% chance. If we are saying it's a 0%, I can take the decision. It could help me, to take a decision based on that. If I say 0% chance winning today, um, India winning the match, then I know where to bet. If I say there's a 100% chance that today India will win, so I know where to bet, right? But the 50% is something, okay, which is not decisive. Okay, I cannot make any decision on that. So how we calculate the probability is simple. Number of outcomes of my interest divided by total number of sample or or the size of the sample or total number of the outcomes. Outcome means, let's suppose there are 10 matches happened. For all the 10 matches, I will measure the outcome. For example, I want to know whether India has won or not. So for example, India has won this match, these 4 matches, and other matches it has lost. What is the probability of winning a match? So it is 4, which is number of wins, divided by total outcomes, which is 10. So which is 40% chance, right? So that's the formula of the probability. So whatever event is of your interest, you will take the count of those events and divide it by the total number of uh, outcomes. Okay, and that will give you the probability. Now there are certain terminologies. Okay, I will stop with this. So first is experiment. Okay, when you have to calculate the probability, generally, yes.
Your screen share is not affected actually. The old one is.
Okay, what happened? Can you see it now?
Yes.
Yes.
Okay. So these are some of the terminologies you have to keep it in mind because when we deal to any probability state problem, okay, generally we talk about all these things. Okay, first is like experiment. I think experiment you are clear with, right? When we are dealing with probability, okay, we generally do certain experiment. So for example, if I want to find out whether particular mm, what we say, with a particular vehicle in a particular condition, it will break down or not. So for that, what I will do is I'll make certain experiments. I'll do certain experiment. So what I will do, I'll take that vehicle and use it in particular condition. I'll not do it only just once. I'll do it multiple times. Okay, and that would be my sample space. So for example, I perform that experiment 10 times. Okay, in that 10 times, I will measure what is the outcome. So let's suppose out of 10 experiments, in 5 experiments, that vehicle broke down. Okay, so that means there is a 50% chance that the vehicle would break in that particular situation. Okay. Now, what is the event here? Event is nothing but that particular experiment, okay, and whatever we are going to test, that is my event. Okay, so that is event. And whatever is the output of that event, that would be my outcome. Now, elementary events. So whatever in each of the experiment, whatever test I'm making, those are known as elementary events. Okay, then comes the sample space. Sample space is whatever number of experiments I'm doing, that will become my sample space. If I'm making 20 experiment, then my sample space is 20. If I'm taking 20 observations randomly, to check, okay, what is the quality of my product, or how many number of objects are defected. So then my sample space would be my sample size. Okay. Unions and intersections. I think you are known with that, right? So if you remember the set theory, for example, this is one sample, this is another sample. So intersection means are those events which are common in both the sets. Okay, and that is known as intersection. Union means it is all the unique events or the unique uh, observations or events in both the sets. Okay, then that is known as union. So all this entire thing is union. Okay. The mutually and exclusive events, this we discussed already. Independent events, I think then if the two events, like these two events, are not overlap, then we called as the independent events. Okay. So for example, rolling a dice, okay, and tossing a coin. Right? These two events are independent. So they are not dependent. So it's not something like, okay, if I get heads, then is a high chance that I will get 6, right, on the dice. So these two events are completely independent. Okay, so those are known as independent events. Now, collectively exhaustive events, complementary events is something, for example, if I'm rolling a die, a particular event is like getting a number as 1. So complementary event would be all those events other than getting 1. Okay, so that means getting 2, 3, 4, 5, and 6. These are considered as the complementary events of 1. Okay, other than that event, from the entire collectively exhaustive events, we'll consider as a complementary events. So if A is an event, then A dash is known as complementary event, which would be equal to 1 minus of A. Okay, all those events other than A is known as complementary events. Okay, all these are definitions. Okay, so more on this we will discuss in the next class. Tomorrow, guys, again, I will inform if I can take the class or not. So please bear with me for this week. Okay, but I'll try my best. If I get late in reaching my place, so probably I may not able to take the class. But go through this class and understand these topics. Okay, and following week, we'll have a regular classes and we will not take any break in between. And I will make sure that, okay, I'll finish this course on time. So don't worry on that part. Okay, so I will inform you on my Teams channel. So yeah, I'll take a pause here. Let me know any questions, guys. How many of you have some idea about probability? All these terms, joint probability, conditional probability. Okay. Saurabh, yes. Anybody else? So it's a very, very interesting topic because I never thought that, okay, this could be that useful, this probability. But trust me, guys, probability is one such topic. If you get master onto this, I think you can make a lot of money. Okay, you will have a better idea of where to invest, how to invest, which will win, what will happen. Okay, so all that kind of power you will get. Okay, and you can take better decisions. And we'll see that how this probability and whatever algorithms we will see in machine learning, most of them are the probabilistic models. Okay, which will predict whether any particular event would occur or not based on these probability calculations. So in that way, in machine learning also, we are going to use probability. Okay, so this would be an interesting topic for you guys. Okay, so if no questions, then I will wrap up for today's session. Okay. All right, guys. Thank you then. Take care. Goodbye.